I'm Hanno Böck. I work as a freelance journalist.
Microphone!
Like this? Okay. You can understand me now? Yes. Yeah, great. I'm Hanno Böck. I work as a freelance journalist. You can read my articles often in German, or I write the bulletproof TLS newsletter if you're interested in everything else about TLS, and from time to time on LWN. And the other thing I do is that I run the fuzzing project, which is an effort I started around 1.5 years ago, where I found out, okay, there's a lot of free software out there that if you run a fuzzing tool on it, you can easily find bugs and security vulnerabilities, and yeah, I want to clean that up and yeah, find ways to make free software more secure. And this effort is now supported by the Linux Foundation's Core Infrastructure Initiative, so yeah, I'm getting paid for doing this. And yeah, but the project I want to tell you about today is not about fuzzing, but it's something which is kind of related. So the typical security vulnerabilities we have today in C code, like buffer overflows, memory corruption, out of bounds reads, use after free errors, they all boil down to a core issue that C doesn't have any intelligence about the memory it uses. You have some kind of buffer, and then you're accessing the buffer for too many bytes or on the wrong index. Yeah, then you have a problem. You have a bug, and it may very well be a security vulnerability. Now, the question is, so if your code does this, if your code reads some invalid memory, that is by the C standard called undefined behavior, which means your compiler can do whatever it wants. You have no guarantee that your code will have any kind of reliable behavior. So we could say, okay, if the compiler can decide to do whatever it wants in these cases, couldn't the compiler say, okay, let's play it safe, and if there's an access to invalid memory, just terminate the application and throw an error. And there have been different attempts to do this. So there's Wallgrind, which probably most of you know. It doesn't terminate the application, but it will detect some of these invalid memory access errors. There's a project called Softbound CETS, which tries to do this in a very strong sense. The problem with it is that it's not really practical. So you can compile a Hello World tool with it, but as soon as you try to compile some real software with it, you end up finding out that it doesn't work. And then there's, since a few years, something called Address Sanitizer, which is a compiler feature, and which is what I'm going to talk about in more detail. So Address Sanitizer is implemented as a flag in GCC and CLang. So you probably all already have it on your machines. It's just yeah, an additional compiler flag. It has a, let's say, acceptable overhead. Your application gets 50 to 100% slower. So this is originally designed as a debugging tool. This is not something which was originally supposed to be run for production use, but to test your software. And the nice thing is it actually works. Like, it's not like a tool where, okay, it's nice, but if you try to compile a real application, then it will break. But most applications, you can compile with it and you can run with it. So this is how it looks like if you compile an application with Address Sanitizer and something bad happens, then you get one of these nice stack traces. So you get a pretty detailed idea of what's going on. It says here it's a write of size 4 at some address, and you get the lines in the code where it happened, and you get a full stack trace where it happens. And you also get an idea where this memory was probably allocated, why. So you get a pretty good idea what your bug might be. So that's a real-world example from a bug in libbsd, that I reported just a week ago, yeah, was a classical buffer overflow. Yeah, but now at some point I asked, so okay, this is a nice feature. Would it actually be possible to compile your whole system with address sanitizer? Because, yeah, for one, it's probably mean that we would find a lot of bugs just by trying that, and it might be an option if you want to have a very secure system that you can kind of accept the overhead that address sanitizer means to run your system. And I tried this with Gentoo, but Gentoo really here is just the kind of the tool I'm using. You can do this with any distribution. I mean, Gentoo is nice because it's already designed to be self-compiled, thereby just adding another compiler flag. So you might think, okay, it's just a compiler flag, let's add it and recompile everything. But it's actually not that easy, unfortunately. So some of the problems are, okay, if you try to compile glibc with address sanitizer, you run into a problem because address sanitizer is actually replacing some of the glibc functions to intercept memory allocations and know what's going on, and there you get kind of recursion problems. You also cannot easily compile GCC. It's both possible to compile glibc and GCC with address sanitizer, but it's not, it doesn't work out of the box. So at least for a start, I said, okay, let's disable them and compile everything else with it. Yeah, then the next problem you run into is that if you combine code with address sanitizer and without address sanitizer, you get some problems. It is no problem to have an application that you compile with address sanitizer and a library that's not compiled with address sanitizer. But the other way around, that doesn't work. So if you think, okay, I will start compiling my OpenSSL with address sanitizer, then immediately all the tools that are linked against OpenSSL won't work anymore. So for one, this means, okay, we have excluded GCC. That means we also have to exclude all the dependencies from GCC. And it also means if you want to recompile everything, we have to consider in which order we do this, so things don't break and we're still able to use the system. Then, which is kind of obvious, it's the point of address sanitizer that when you're accessing some invalid memory, that your application crashes and throws an error. So if you have an application that just does this in its normal operation, which is quite common, yeah, then you have a problem, so you have to fix these bugs first. And I reported a lot of these bugs. I've listed some tools here which are kind of core features of most Linux distributions. So Bash was crashing all the time when you tried to do tab completion. Then I had a bug in Shred, which was interesting because it was at random. So Shred has a feature that it generates some random pattern in memory, and this is random, and in 1/4 of the cases it would access invalid memory. Yeah, ManDB had a use after free bug, and yeah, all kinds of these things. So these need to be fixed in order to be able to use the code with address sanitizer enabled. But it's a good thing we fix bugs. Then this is something which is difficult. Sometimes you see code where the code documents that the code is wrong. Or you have people who say, okay, this cannot be, my code is correct, it must be a bug in address sanitizer. I'll show you an example. This is code from Subversion, the current release. So it has an if-def, no uninitialized access. So the correct code is optional. So yeah, it says, yeah, this may read allocated uninitialized bytes beyond the terminate email, which is wrong. The bytes are actually not allocated. I had some discussions with the developers, and in the end they fixed it. So turned out good. This example is LuaJIT. It actually says two things that indicate that the code is wrong. One, it says that it's unaligned access, which is also technically not allowed, but it's very common. And the next is here, it says access up to end of string +3. Where the discussion was a bit more difficult. I mean, you probably know this with free software developers. Most of them are nice and some are difficult. Yeah, so I don't think they intend to fix it. Yeah, this kind of code is not correct. So you cannot just read some memory and expect that you can do this. It might very well be that you're not allowed to access this memory, or it might very well be that your compiler decides to do, to say, okay, this is accessing invalid memory, so I can ignore this state because it's invalid, so I can optimize it out. And it's actually very rare that address sanitizer has bugs, so I haven't found any. So if someone says it must be a bug in address sanitizer, I'm very skeptical. And there may be false positives, but it's really rare. Yeah, then I had all kinds of compile issues. One of them was that libtool, when you link a shared library with libtool, it filters the linker flags, and it says, okay, I will only allow linker flags that I know that are good. And this ends up breaking a build with address sanitizer, because address sanitizer needs to link against the lib-asan, and thereby if you strip the address sanitizer flag from the linking step, then the linking fails. This has now been fixed. There's no release yet. But the kind of tricky thing is that libtool it's not that you're using the libtool that's installed on your system, but the libtool scripts are bundled with packages. So in order to deploy this fix, it will take some time, because I basically have to get the libtool update on the computers of the developers of the affected applications. And this was so common that what I actually did was that I added a function hook to Portage that looks for these scripts and patches them on all packages. Yeah. Then this was kind of tricky to debug actually what was going on. So with libpthread, the problem here is that the address sanitizer library is providing some pthread functions because it's hooking them to record what memory is accessed, but not all of them. So what happens is that if a configure script checks if pthread create exists, and it says, okay, this function exists, I don't need to link the library in because it's already available. But then the compilation breaks because the other functions are not available. Yeah. I'm still not really sure what the best solution for this is. If anyone has a smart idea, this problem was present in SQLite, and I sent a patch to check for another function, but then a few days later someone complained that this would break on FreeBSD. I don't know why. Okay, thanks. I should go faster. Yeah, then a tricky issue was with Perl. They are using LD preload to load the already built libperl and then run a mini-perl to run their own compile script. And if you preload an address sanitizer library and then try to execute GCC, which is not compiled with address sanitizer, it's like false. There also, if anyone has a good idea how to fix this in a way that Perl would accept the patch, I would be happy, because it's really tricky and I don't have a good idea how to fix it. Yeah, then, okay, so we can have a system that's compiled with address sanitizer. You have to expect a lot of breakage and you have to be prepared to fix bugs, but actually, why is this useful? So, okay, we find bugs, that's useful, of course. We get software with less bugs. But then you might ask, okay, is this really something I want to run like on a server where I say, okay, I want to have a very high security guarantee? And it's not entirely clear if this is a good idea to me. So there's currently the Tor project also playing with this. They want to have a Tor hardened browser with address sanitizer enabled. So there are already other people who are trying to use this in production code. But address sanitizer was originally mostly designed as a debugging tool, so it's not necessarily the best to prevent exploitation. So it prevents some bugs from being exploited, but if you have what you can call a linear buffer overflow, so if you have a buffer overflow that's starting inside your existing buffer but goes beyond the bounds, then these bugs are reliably caught by address sanitizer. But if you have a buffer overflow where you can kind of jump out of your buffer, this may still be exploitable. And also use after free errors are found by address sanitizer, but you may still be able to exploit them anyway. There's a blog post from Chris Evans where he's explaining in much detail how good address sanitizer might be as an exploit mitigation tool. And then it might be that address sanitizer itself has bugs that lead to exploitation, so you might introduce other security issues. But I still think this is a useful project, because maybe even if this is mostly useful as a debugging tool, maybe in the future we'll have something like address sanitizer that's much better, that maybe has hardware support, maybe has reasonable performance that we can use. And if we want to even think about this, we have to fix these bugs where standard applications are accessing invalid memory. And I mean, the other thing that exists is various exploit mitigation techniques. I find it very unfortunate that ASLR is still pretty much not enabled on common Linux distributions. There's some interesting work on new exploit mitigation techniques. LLVM has now code flow integrity and safe stack features, which, probably if right now you want to use something for production, these things are probably more interesting. And then I have some more slides if I have enough time, but I probably don't. 1 minute, yeah. Okay, so address sanitizer has a logging feature, which is nice if you have an application that disables your standard output and standard error, because then you cannot see the error message. So it's very useful. There are more sanitizer features in the compilers. Undefined behavior sanitizer, which is mostly shifts and unsigned integer overflows. Thread sanitizer and msun, which is for uninitialized memory access. And this is an example for a bug I found like a week ago or something. This was the libbsd bug where I showed the stack trace earlier. Actually, what's happening here is that the bigger must be a bigger or equal, because it's checking if we're still in the buffer, and if the size is the index, then we're already out of the buffer. So very typical off by one bug. Yeah.
Thank you. Questions? Raise your hand if you want to ask a question.
I would like to ask, you said the initiative to compile also the
it is possible to compile with sanitizer, but it is mostly independent. So it's possible.
There you go. That was my question.
Okay. But the problem with that is that it only logs the errors and doesn't flush over them. So you would want to, but you could probably cache that.
So how useful was the Jenkins system then after all if you couldn't run Perl?
I could run Perl, but I had to have a hacking workaround.
Could you actually use it to, say, browse the web?
Browse the web? No, I haven't tried with the browser so much, but I have running it in the server, so I can surf my pages.
Yeah, and I'm also wondering whether there's, say, a second level addressing it with, like, you know, complex software tends to have their own allocated EMIs.
Yeah, that doesn't. If they have their own allocators, you have to disable them.
So essentially,
yeah,
it's really hard to know and essentially have a complex software.
So I mean, this was developed by the Chromium developers basically, and they have an option to disable their whatever TCM or whatever it's called. So most of these, like also Firefox, you can also compile with address sanitizer. It's not straightforward, but it's used. So usually what they do is they disable their
So from what I've seen, the address intelligence looks similar to Valgrind in terms of memory usage information. So in which way does it help you more than Valgrind?
It's much faster and it finds stack overflows. Valgrind cannot find stack overflows by definition because the stack is just a bunch of memory in the binary. It doesn't have the information to find stack overflows.
Thanks.
I have a question about the protection of the P3 trade when using libasam. Can you use those P3 to be linked into the library address? Can you use instead force that link P3 is
yeah, I can do that, but that's kind of an ugly workaround. So I want things to just work if you enable this.
More questions?
My question is, most of the time I would just use defense to see where my program would write in or read where I'm not supposed to go to. So most of the time it's efficient enough to find the bugs. Why would I want to use address sanitizer? The production mode, can't I just use this or whatever equivalent tool there is in a program in developing mode, and when I'm good to go in production mode, disable.
So I'm not familiar with libfence. I know the name and it's something similar, but I don't know the details. But what was your question? Like
okay,
you test the address sanitizer and use it without in production.
Yeah, or is there a reason why I would want to use it in production?
Yeah, if there's a bug you don't know about, then it might prevent exploitation of that bug. Yes. So you increase the risk for denial of service, but you lower the risk for owning your machine.
It's a coverage protocol. You cannot test all the coverage.
And of course, there is one. Thank you, Hanno.